Alright, hello everybody. It's a beautiful day outside today. The sun is out, the weather is warm, the slight breeze is blowing, and I'm doing calculus. Well, what do you know about that? I am here to show you the second of three parts that we're going to learn before the end of the year. Now I'm going to actually break the second part up into two smaller parts, because now we're going to find volumes of three-dimensional objects using calculus. If you remember, the basic formula for volume in geometry was for any prism, it was just the area of the base times the height. For example, you had a cylinder. Well, what's the base shape of a cylinder? Well, it's a circle. What's the area of a circle? It's pi r squared. And the height is h. So it's the area of the base times the height. If you just take a rectangular prism, which is my fancy way of saying box, and assuming the box is actually nice and not crooked like that, we used to do length, width, and height. Well, what's the area of the bottom? Well, it's length times width, and then we multiplied it by the height. It's like we took that bottom shape right there, and we just kept building on top of each other and building and building and building. And what eventually would happen is we would stack it up and we would make ourselves a box. Now that's the geometry part of it. So all we had to know was what was that basic shape that made the three-dimensional object. In the cylinder, it was a circle. In the rectangular prism, it was a rectangle. So that leads us to our formulas for volume with calculus. And here they are. I'm going to give you two. It's really the same formula, but I'm going to show you why I'm going to give you two. The volume is the integral from A to B of the area of the cross-section. And the area of the cross-section has to be written as a function. And we'll see examples why. Now sometimes we do it with respect to x, and sometimes we do it with respect to y, and I will show you those two reasons, or those two examples, and how you differentiate between the two. That's why I said there's two formulas, but there's really just one. You're taking the integral of the area of the cross-section. So when you think about a second what that means, if I take the area of the cross-section, like this circle, this integral means from A to B. It means I'm going to start at the bottom, and I'm just going to keep building it up and up and up and up and up and up. I'm going to go from A to B. So the integral from A to B actually represents the height of your object. Remember, height is a relative term. I don't know if the thing's standing up, lying on its side, diagonally leaning off of something. It doesn't matter. Remember, height is just the distance from both sides, both ends of the shape. Okay? Cylinder, circle on top, circle on bottom. The height is the distance in between. So take a look at this graph. You've got two curves. We'll call this red one F and this blue one G, and they intersect at 0, 0 and at 1, 1. What we did last time is we found the area between those two curves. So we just took the integral from 0 to 1 of the top function minus the bottom function. We gave us that distance that was in blue. And the idea was, as you moved along the x-axis, that did change shape from smaller to bigger, wider, and it gets smaller again. But that always represented the distance between f and g, okay, between those two functions. Now we're going to throw a third dimension in there for you. I'm going to rotate this on its axis. So what I have done is I have built a square on top of, if you want to call it top, whatever direction you want to go, but I built a square on that intersection. The square has the dimensions of the distance between the intersections. And what I mean by that is if I get closer to the end, where the graphs are closer together, the square gets smaller. The base of the square is always the distance between the two graphs. And that creates a three-dimensional shape. So I will show you that three-dimensional shape right now. The more squares I have, the more accurate my answer is. If I take all those squares and I find the volume of all of the rectangular prisms that are made from those squares, and I add them together. That's representation of the volume. Therefore, the volume of any function in calculus is the integral of the area. We take the cross-section, we find the area of that cross-section, we integrate it from, in this case, 0 to 1, whatever our beginning and ending point is, and then we've created a three-dimensional object. Entirely built of squares. So to put this into calculus terms, the volume, which was the integral from a to b of the area of the cross-section. Now if this was a square, the area of the cross-section would be this distance squared, because remember the area of a square is side squared. This distance here represents one of the sides. And the height, we're going from 0 to 1. Now this particular distance from here to here was the function of f minus the function of g squared with respect to x. This formula here would give us the volume of this shape here. Now if you remember in my classroom, I don't know if you guys ever saw the ones that were built. Those were actual three-dimensional models that were built by students that we didn't get a chance to do this year because we're not meeting. But like I said, it doesn't matter if you can visualize the three-dimensional shape. Can you use it? So let's start using them and see what's going on. All right, I've given you two graphs. Y equals 2 roots of x plus 1 and y equals 1/2 x squared plus 1. They are graphed right here, and I have given you their intersection points. Question, what's the volume if the cross-section perpendicular to the x-axis are squares? Now I'm saying the x-axis, and there's a reason I'm doing the x-axis, because later we're doing the y-axis. But if it's perpendicular to the x-axis, notice the distance between the two graphs is the distance from that graph to that graph. It's a y distance, but it's in terms of x. So can you write the expression for that graph? Remember, this is, according to the visual you just saw, that's the bottom of the square. The area of the square would be that bottom squared, because the area of a square is side squared. What I need is an expression for that s. Now because we're going perpendicular to the x-axis, we're looking at our x values between 0 and 2.52. The x values. The side is going to be represented by this colorblind, this red graph, which is 2 root of x plus 1, subtracting the blue graph, which is 1/2 x squared plus 1 squared. It's this distance squared. Squared because that's the area of a square. You take the side and you square it. Now I don't want you to do this by hand by any stretch of the imagination. I want you to put that in your calculators and estimate the answer. And when you do that, because I've already done it, I get the answer 3.266. That's the volume of the three-dimensional shape created by doing a cross-section of squares. So again, you don't have to visualize what the shape looks like. Most of the time, I don't even bother. I just know I need the cross-section, and I need to know what shape I'm making. That's it. We're going to use the same shape with different cross-sections. Now we're doing semicircles. But remember, perpendicular to the x-axis, so isn't this still going to be the red function minus the blue function? Now here is what semicircles look like. So remember, between each function, we're graphing a semicircle. And again, the semicircle gets smaller at the ends because the distance is smaller, gets wider towards the middle, and then at the end it gets close to 0 again. So what does that shape look like? Well, let's take a look. If I throw a whole bunch of semicircles in there, almost looks like maybe a canoe. We turn it upside down and look at that part. Well, I guess I can't turn it upside down. That's the limits of what I can rotate. Not a very good canoe because it's solid. I mean, that's a solid piece there. There's nothing carved out. But that's what that shape looks like. This distance here represents the diameter of that circle. All right, what's the area for the semicircle? Well, pi r squared is a circle, and the semicircle is half that much. So it's the volume. Now the 1/2 pi is a constant. I'm just going to take those out front because I can. My height, which I don't have, it's going to be from 0 to 2.52. Remember, that's the expression for the height. We're going from 0 to 2.52. I need to know the expression for the radius. Well, remember, if this is the diameter, the radius would be half of that. The diameter is the distance between these two graphs. So we got to take the distance of those two graphs, divide it by 2, and then square it. Remember, because our radius is going to equal this. Our radius is going to be 2 roots of x plus 1 minus 1/2 x squared plus 1. Now that's our diameter. We need to take half of that diameter. And then what do we do with that radius? We square it. All right, not the most fun thing to put in a calculator, but if you do, this is what you get. And you get 1.282 approximately. All right. Just so you know, the semicircle is probably the nastiest parts because there's a lot of halves. But now we're doing a rectangle with a height of 3. We know the area of a rectangle is just base times height, so it's 3 times whatever the base is. Okay, well remember the base perpendicular to the x-axis, so the base is this distance between those two. So the volume would be the integral, well, 3 is your constant, we'll pull the 3 out. The integral of from 0 to 2.52 of the expression for the base. Well, remember, that's the expression for the base. We've built a rectangle on top of this. It has that as a base, and it's 3 units tall. You can't see it because it comes right out at you, but it's 3 units tall. So there's your 3 units tall, and your base is just going to be the same old thing. It's the distance between those two graphs. There's no squaring or anything this time. It's just 3 times the base. Here's your 3, here's your base. All right, put that in the calculator and you get the answer of 8. What do you think so far? Okay. And now we're doing equilateral triangle. And here's what an equilateral triangle would look like in this case. So the equilateral triangle, again, the base, the side of the equilateral triangle is dependent upon the distance between those two curves. As curves get closer together, the triangle gets smaller. What would that shape look like? Well, let's take a look. If I build a whole bunch of triangles on it, I end up with a shape kind of like that. Alright. Now the nice part is, I'm going to go back to this view, you don't have to visualize it necessarily to understand how to do the volume. If you know the distance is between these two curves, all you have to know is that distance, which in this case will be the value of f minus the value of g. And that will give you any three-dimensional shape that you want to put on top of it, a square, an equilateral triangle, or a semicircle. In all my years of teaching geometry, I have never, ever taught the volume or the area formula for equilateral triangles. The only time I ever use it is when I'm in calculus class. So maybe it's something you're supposed to learn. Maybe you learned this, that the equilateral triangle area is the square root of 3 over 4 times the side of the triangle squared. So that's the side of the equilateral triangle. Let's find its volume. Alright, it's square root of 3 over 4 from 0 to 2.52 of the expression for the side squared. Remember, the side of this, the distance is the distance. The length of this is the distance between the two graphs. So yet again, it's 2 roots of x plus 1 minus 1/2 x squared plus 1. That whole quantity is squared dx. Put it in the calculator, you get 1.414. All right. Now my next example, I'm switching one thing. I'm keeping the same graphs, but I am switching from the x-axis to the y-axis. Now I'm going to say, hey, let's take the square, but the distances would be this direction. So I'm going to have all these squares that are built this direction. Now, will that be the same exact shape? No, it'll look different. Will it have a different volume? It should. It should not be exact, but you know what? We're going to find out, aren't we? So here we go. There's one thing we have to be careful of. All right, and that thing that we have to be careful of is this. If we want cross-sections perpendicular to the y-axis, so if we want to do the cross-sections perpendicular to the y-axis, we have to put our equations in terms of y. Right now they're in terms of x. So let's solve for x and see what we need to do. Let's see if we can do this pretty easily. All right, I'd have to subtract 1 from both sides. So y minus 1, then divide by 2. And then the opposite of square rooting would be a square. So this equation, written in terms of x, is that. Those are the same equations. And same with this, we've got to solve this one for x. So I have to subtract 1, then multiply by 2. So I will get, let's see, subtract 1, multiply by 2. So I will get 2y minus 2. And then x squared, the opposite of squaring, is that. So now we have two new expressions. They're the same graph, but just written differently. Because remember, if I'm looking for this distance, that's a horizontal distance. That's an x distance. So to find the x values, I got to put them in terms of y. All right. Area is still going to be the side squared. So the volume is going to be the expression for the side. Now the expression for the side now has changed. I want to do the graph furthest away from the axis. I'm going to do this blue graph. And this blue graph happens to be 2y minus 2 minus the red graph, which is y minus 1 over 2 squared. I'm going to take all that and I'm going to square it. Remember, this is the expression for the side. I'm going to square it. Now, I didn't put the limits of integration yet because I'm doing my y-axis. Now I'm going to use the y values. I'm going from 1 up to 4.175. That's what I have to solve. And when I put that in the calculator, I get 2.592. Okay, so you see the steps. Whatever my cross-section is perpendicular to, those are the variables that I'm going to be using. So if it's perpendicular to the y-axis, I put things in terms of y. Perpendicular to the x-axis, I put things in terms of x. The only two things you really have to know then, what's my formula for my cross-section, and what's my expression that will fill out that formula. Okay? So, semicircles. Remember, cross-section is perpendicular to the y-axis. So here's the bottom of my semicircle. And remember, semicircles, 1/2 pi r squared. Okay. The volume is going to be the integral of this. Well, the 1/2 pi can come out. The integral in terms of y, remember, are going to be from 1 to 4.175. All right, now I'm going to take my radius. Remember, this is my diameter. It's the whole way across. I need half of that. So again, that distance is going to be the square root of 2y minus 2 minus y minus 1 over 2 squared. Right? That's my distance, but I want half of it. Then what I'm going to do with that whole thing, I'm going to square it. Again, I'm sorry for the ugliness of that one. but, you know, school's almost over. We can do a couple ugly problems, right? All right, let's calculate that answer. Volume of 1.018. All right. And these are a little weird. Take a little getting used to. Remember the steps. Look at the cross sections which are perpendicular to. Draw a little line that's perpendicular to that axis. Oh, see, I got to find the distance between those two graphs right there. I'm looking for the cross section that's a rectangle, and the area of the rectangle, remember, is base times height. Well, I know in this case my height is 3. So it's going to be 3 times the base. Well, this is the base, that expression. So my volume will be the integral of this. It'll be integral of 3 times the base. Well, since 3 is a constant, I'll pull it out. You don't have to. You can leave it inside if you want to, but I'll take it to the outside of the integral sign. The y values are going from 1 to 4.175. And what is the expression for this distance? Well, the blue graph minus the red graph. So the blue graph is square root of 2y minus 2 minus the red graph, which is y minus 1 over 2 squared. With respect to y, put it in your calculator, and you get the answer of 8. Now that is interesting. I believe that's the same answer we got for the rectangles going the other direction. So, yeah, 8. So I wonder if there's a correlation there. Seems coincidental. So it might be. It would merit further study, but for today, I'm not going to worry about it. I am just going to continue on with the last problem. Equilateral triangles. Remember that really weird formula for equilateral triangles is the square root of 3/4 side squared. Cross sections are to the y-axis. So this is, even though I can't tell, I can't see it three-dimensionally, that's the base of my triangle. So that's the base, which we call the side. Okay. The volume will be the integral of this. So the square root of 3/4 being a constant, I will pull it out in front of the integral sign. We're going from 1 to 4.175, and the expression for side are the difference between the two graphs. So again, 2y minus 2 square root, and subtract the other graph, which is y minus 1 over 2 squared. Now we're squaring this one, and look what we have here. We have square root of 3/4 side squared. And then we just calculate that. And in this case, this answer is 1.122. All right. That's probably a lot to take into right now. It's a lot of visualization. So we'll have a live session. We'll talk about this one. That will be on Tuesday. Our next live session will be Thursday. We'll talk about the second part of it. And we'll have a live section again the following Tuesday, which will be going over the last section. That'll be it. That'll be it. And we'll all be done. As soon as you guys get me that test, I release you from calculus for this year. But let's hang in there a little bit longer. So I hope you have a great day, and I'll talk to you soon. Bye.